Good morning, all of you. Welcome to Sri Jayendra Rank Zone. Today, we're going to discuss new lecture in states of matter. That is lecture 2. In the first lecture, we have done all the gas laws along with ideal gas equation. So now, I'm going to do the next topic in this chapter. Now we are going to do in the first lecture. We didn't get time to do numericals. So now we are going to do numericals in this chapter based on gas laws. After that, we'll discuss new topic. So new topic based on gas laws. We have numericals now. So we are going to discuss that. So coming to first numerical, a gas occupies a volume of a gas occupies a volume of 2.5 decimeter cube at 9 to 10 to the power 5 pascals. So they have given volume as well as they have given pressure. Calculate the additional pressure required. So they are asking, so this is P1, is V1, and additional pressure is P2 required to decrease the volume of the gas to 1.5 decimeter cube. So volume they have given, V2 is given. So this is V1, this is V2, keeping the temperature constant. So keeping the temperature constant, we have to discuss. This is purely application of Boyle's law, since we know from Boyle's law we know P is proportional to 1 by V, implies P1 V1 is equal to PV is equal to constant, and P1 V1 is equal to P2 V2. Now simply we have to apply this formula. So they are given P1, that is equal to 9 10 to the power 5 pascals, into V1, that is equal to 2.5 decimeter cube. They are given in liters, both liters, no need to change the unit, is equal to P2 we have to find, into additional pressure P2 we have to find, into volume is given how much? Volume is equal to 1.5. So by this you can write P2 is equal to 9 into 10 to the power 5 into 1.5 into 2.5 divided by 1.5. It's very simple. So by substituting this, you'll get the answer. So I hope it is clear. So this becomes 6 into all 2.5. So that calculation part I will not do, so you can understand it. So easy it is. This is basic level 1 question. So it is equal to 6 into 10 to the power 5 pascals. So I hope it is clear. It is equal to 6 into 10 to the power 5 pascals. So you can use that. Next question, question number 2. A balloon is filled with hydrogen at room temperature. It will burst if pressure exceeds 0.2 bars. So this is given as pressure. If pressure exceeds 0.2 bars, the balloon will burst. If at 1 bar pressure, the gas occupies 0.27 liters, up to what volume can the balloon be expanded? So here also the same formula, P1, and this is P2, because 0.2 bars if the pressure exceeds, and V1 and V2. So we have to find V2 over here. So P1 V1 is equal to P2 V2. So by applying this formula, you can find out what volume can the balloon be expanded. So the balloon can be expanded up to what volume. You have to substitute the answer. So after calculating that, you'll get the answer. So P1 V1 is equal to P2 V2. So it is equal to 1.35 liters. So P1 is 0.2, P2 is 1, and P1 is equal to 0. The balloon is filled with hydrogen at room temperature. It will burst if the pressure exceeds 0.2. So it is pressure is P2 is this 0.2, P1 is 1 bar, and V1 is 0.27 liters. Finally, we have to find V2 V2. So easily you can understand this question. Next question. When a ship is sailing in a Pacific Ocean where temperature is 23.4 degrees C, a balloon is filled with 2 liters of air. These are all NCERT problems. So when a ship is sailing in Pacific Ocean, when the temperature is 23.4 degrees C, a balloon is filled with 2 liters of air. What will be the volume of the balloon when the ship reaches Indian Ocean where the temperature is 26.1 degrees C? So automatically here volume is temperature is increasing from 23.4 to 26.1, because from Pacific Ocean the temperature is changed to Indian Ocean. If the ship has reached to Indian Ocean, automatically the temperature will change, and keeping the pressure constant because it is atmospheric pressure, and it is filled with 2 liters of air. So as the temperature increases, definitely volume of the balloon also increases. So but here very important thing is they have given the temperature in degrees C. From Boyle's law we know volume is proportional to absolute temperature. So we have to consider into We have to change this degrees into both degrees into Kelvin temperature. So T1 is equal to 23.4 plus 273, sorry, and T2 is equal to 26.1 plus 273. We have to compulsory confirm because the volume is proportional to absolute temperature. So definitely we have to change the given temperature in degrees C to Kelvin temperature. Then only you'll get the correct answers. So T1 is equal to 23.4 plus 273. T2 is equal to 26.1 plus 273. So you'll get T1 values, T2 values. That is 273 plus 23 is how much? 296. 273 plus 23 is 296.4 kelvins. And 26.1 plus 273 is 290. So it is 299.1 kelvins. So the temperature is raised. So volume is V1 becomes how much? V1 is 2 liters, and V2 we have to find. V2 is equal to how much? So simply by applying Charles' law, we can find out the formula. So V1 by T1 is equal to V2 by T2. So apply this formula, definitely you'll get the answer. I hope it is clear. So definitely the volume will increase more than 2 liters because of the temperature is increased. So answer will be 2.01822 liters. So slightly more than 2 liters. I hope it is clear because temperature increased slightly from 23.4 to 26.1. So use this formula, you'll get the answer. I hope it is clear. Next question. At what temperature will the volume of the gas at STP double itself, pressure remaining constant? Here this is constant, it is not content. It is a printing mistake. It is pressure remaining constant. So again, this is an application of Charles' law. So at what volume? So V1 is given as what volume? The volume of a gas at STP double itself. So take V1 is equal to V and V2 is equal to V because volume is doubled. And T1 is equal to standard temperature STP. STP means standard temperature is 273 kelvins. And T2 becomes volume of gas at STP double. T2 how much? So we have to find the temperature in kelvins in T2 case. So even if they are given in degree C also, you can find the temperature in kelvins. Then you have to convert them into degree C. So for this, we can take V by 2V is equal to, sorry, V1 by T1 is equal to V2 by T2. So V1 by T1 is equal to, by applying Charles' law, V2 by T2. So it implies V1 is equal to V by T1 is equal to 273 is equal to V2 is equal to 2V by T2 is T2. So by this we can take V and V gets cancelled. So implies T2 is equal to 273 into 2. It is equal to 546 kelvins. I hope it is clear. So at what temperature will the volume of a gas at STP double itself? Double itself. So take V2 is equal to V, keeping pressure constant. So answer is 546 kelvins. So if they are given the answer in degrees C, you can take 546 minus 273. So answer could be 273 degrees C. Even this for this the same answer will be 273 degrees C. Either it can be 546 kelvins or 273 degrees C. Both are same values. I hope it is clear. Next question. So you can see 546 kelvins are 273 degrees C. Next question. A flask has a capacity of 1 liter. What volume of air will escape from the flask if it is heated from 27 degrees C to 37 degrees? Clearly, it has the flask has 1 liter capacity. What volume of air will escape? What volume of air escape if the flask is heated from 27 degrees C to 37 degrees C? So take this is V1 is equal to 1 liter. So you can take by applying Charles' law. So this is taken as V1 and T1, T2. We need to find V2. And T1 should be taken as T1 is equal to 273 plus 27. Always you have to change the temperature into kelvins because at constant temperature, the volume of a given mass of a gas is proportional to its absolute temperature. That is Charles' law. So T2 is equal to 273 plus 37, which is equal to 310 kelvins. I hope it is clear. Now you can substitute the formula and you can find the volume. So volume of air will escape from if the temperature is heated. If the temperature increase, some volume will be escaped. So that volume is 33 ml. You can find out the volume. So you have to change the volume into liters into ml so that you'll get the answer. Next question. A gas at 0 degrees C and 1 atmospheric pressure occupies 2.5 liters. So gas at 0 degrees C, temperature is given, pressure is given, and volume is given. At what change in temperature would be necessary if the pressure is to be adjusted to 1.5 atmospheres and the gas has been transformed to 2-liter flask? So volume is increased container. So they are asking what change in temperature. So we know from ideal gas equation. From ideal gas equation, we know the formula by combining the three laws. P1 V1 by T1 is equal to P2 V2 by T2. Direct formula P1 V1 by T1 is equal to P2 V2 by T2, where P1 is called, this is P1, this is T1. T1 should be equal to 273 kelvins because 0 degrees C, P1, T1 and V1. And now we have to find what temperature, that is T2 we have to find in kelvins, would be necessary if the pressure is to be adjusted in 1.5 to 1.5 atmospheres pressure P2 and volume is V2. So substituting this formula, so P1 is equal to 1 into V1 is equal to 2.5 liters by T1 is equal to 273 kelvins because 0 degrees C is equal to P2. P2 is 1.5 atmospheres and volume is given 2 liters by T2. T2 we have to substitute. Implies T2 is equal to 1.5 into 2, that is 3 into 273. This 273 will go this side, divided by 2.5 into 1. So you'll get the answer. By substituting these values, you'll get the answer temperature in kelvins. If they have given the answer in degrees C, you have to change the Kelvin into degrees C by doing minus 273. I hope it is clear. So it is given directly in Kelvin, so 327.6 Kelvins. So at what temperature would be necessary if the pressure is to be adjusted to 1 point? So pressure is increased, volume is decreased, so temperature is also decreased. That is, sorry, increased here, 327.6 Kelvins. I hope it is clear. Next question. Calculate the weight of methane in a 9-liter cylinder at 16 atmospheres and 27 degrees C. This is the application of ideal gas equation. What is ideal gas equation? PV is equal to nRT, where N is equal to weight by molecular weight, and R is equal to gas constant and T is equal to temperature. So by substituting this formula, here they are given, volume is given, pressure is given, and temperature is given. So PV is equal to nRT. Molecular weight of methane, we know methane formula is CH4. So CH4 means molecular weight is equal to, implies molecular weight of methane is equal to 12 plus 4, it is equal to 16. Now by substituting this formula, we can know. So weight we have to find after you. So PV is equal to weight. We know this, we have to find this weight. So is equal to, so P is equal to how much given? 16 atmospheres. And V is equal to 9 liters. 16 into 9 is equal to weight by molecular weight of methane is 16 into R value 0.0821, they have given already 0.0821 into temperature value is given 27 degrees C, 27 plus 273. So temperature is equal to 27 plus 273. So it is equal to 300 kelvins. 300 kelvins. Always you have to change the temperature into kelvins. So by this you can say W is equal to 16 into 9 divided by 0.0821 into 300. So after doing calculation, you will get the answer. I hope it is clear. So let us see the answer. So PV is equal to W by MRT. So answer is 93.554 grams. So here I am writing the answer. It is equal to 93.54 grams of methane is present in that. So I hope it is clear. Next question. At 25 degrees C and 760 mm of mercury pressure. So here they are given T1. A gas occupies 600 ml. volume. So they are given T1, again they are given P1, they are given V1. At what will be its pressure at a height where temperature is 10 degrees C? So T2 they have given, and they have given volume also V2. So pressure is decreased at a height. So how much pressure it is, we have to check it out. So use the same formula, that is from ideal gas equation, P1 V1 by T1 is equal to P2 V2 by T2. From this you have to find pressure P2. And you have to change the temperature in 25 degrees C into Kelvin's temperature. So T1 is equal to, take the values of T1 is equal to 273 plus 25, that is equal to 298 Kelvins, and T2 is equal to 10 degrees C. So 273 plus 10, because they are going T2 degrees C, it is equal to 283 Kelvins. So use this formula and find out P2. Use this formula and find out P2. You'll get the answer 100%. I hope it is clear. So let us check the answer, what the answer will be. So it is 676.6 mm of Hg. 676.6 mm of Hg means, so the pressure is slightly decreased because volume is increased and temperature is decreased. I hope it is clear. Next question. So before going to this, I would like to give one more important question. So I have to give one more important question. I'll write it here. I'll take new slide, new sharing. So these are the problems related to Boyle's law and Charles' law and ideal gas equation. Next, we'll do some more based on this. So next gas laws we have. Avogadro's law. So before going to Avogadro's law, I would like to give one more important question based on ideal gas equation. So since already we know PV is equal to nRT, we don't have NRS, right? So that's why I'm writing here. Since already we know from ideal gas equation PV is equal to nRT, since N is equal to weight by molecular weight, where N is equal to weight by molecular weight or mass of a substance. So by this you can write PV is equal to nRT, that is PV is equal to weight by molecular weight into R into T. And even you can take N also straight away instead of taking, so directly I'll write P is equal to nRT by V. And since implies P is equal to N by V into R into T, this N by V is taken as molarity because number of moles by volume of solution liters. Since N by V is equal to molarity, this we have done in first chapter, that is basic concept of chemistry. So we can write, by this you can write P is equal to MRT, because N is equal to, by this you can write molarity is equal to RT by P. So since N by V is equal to, so even you can do this also from ideal gas equation, and D is equal, density is equal to mass by volume. So we can take density D is equal to PM by RT, where P is called molecular weight. I'll show you this also. Since PV is equal to nRT, N is equal to weight by molecular weight, that is weight is small w, small m, and R into T, which can be represented as small m by molecular weight is capital M into R into T. So by this you can write P is equal to small m by V into 1 by capital M into R into T. By this you can write implies, since M by V is equal to mass by volume is equal to density, we can write P is equal to dRT, implies dRT by M, implies D is equal to PM by RT. where m is here is equal, where m is equal to molecular weight. M is equal to molecular weight. So we can find out the density also. We can find out the density also by using pressure and temperature values. So let us see one example for this. Calculate the density of sulfur dioxide gas at STP. At STP. So simple, density is equal to, since D is equal to P into M by R into T. So P is equal to pressure. So standard pressure is 1 atmosphere. Molecular weight of sulfur dioxide 64 divided by R value 0.0821 into temperature is 273 kelvins. So in this way, you'll get density also. So this is another important model which I want to discuss with you. So that's why I have given here. So D is equal to PM by RT. I hope it is clear now. Next. So in this session, we have done already problems related to Boyle's law, Charles' law, as well as ideal gas equation. Now we'll see next topic in this chapter, that is Avogadro's law. So this law states that under similar conditions of temperature and pressure, equal volumes of all gases contain equal number of molecules. Under similar conditions of temperature and pressure, equal volume of all gases contains equal number of molecules. What does it imply? At constant temperature and pressure, volume of the given mass of a gas is directly proportional to the number of moles of the gas. So this is called number of moles. Based on this one, we have done mole concept also. So for example, hydrogen gas combines Cl2 gas to form 2HCl. So for this, we can say 1 mole of hydrogen gas, 1 mole of chlorine gas combines to form 2 moles of HCl gas in terms of molarity, moles of HCl gas in terms of number of moles. The same way, you can take 1 volume plus 1 volume gives rise to 2 volumes of HCl. Directly, we can relate the number of moles to volume, because since V is proportional to number of moles, this is N values. So since V is proportional to number of moles, so directly we can relate the volume into number of moles. Or V is equal to K into N, K is equal to constant of proportionality. So that's why we can apply the same concept, Avogadro's law, in mole concept. So directly by using the stoichiometric coefficient, for example, 2 moles of sulfur dioxide plus 1 mole of oxygen forms together to form 2 moles of sulfur dioxide. Then we can write 2 volumes directly, 1 volume directly, 2 volumes of sulfur dioxide. So directly volume is, we can write volume because volume is proportional to number of moles. So this we'll use in that case mole concept. I hope it is clear. So according to Avogadro's law, at constant temperature and pressure, the volume of the given mass of a gas, the volume of a given mass of a gas is directly proportional to the number of moles of the gas. As the number of moles increases, volume of the gas also increases. I hope it is clear. This is called Avogadro's law. So Avogadro number is the number of molecules in 1 mole of a gas is equal to 0.63 to 6.022 in 10 to the power of 23. This number is equal to the number of atoms present in exactly 12 grams of carbon-12 isotope. So the number of atoms present in 12 grams of carbon-12 isotope is equal to Avogadro number. Next, what is molar volume of the gas? The molar volume of a gas is defined as the volume occupied by 1 mole of a gas at a given condition of temperature and pressure. So at STP, the molar volume of a gas is 22.4 liters, because 1 mole of a gas at STP occupies 1 mole of a gas at STP occupies 22.4 liters, or 22,400 cc, or 22,400 ml. Similarly, at STP means is equal to 1 atmosphere and 273.15 kelvins, or 1 bar and 273.15 kelvins. It is slightly reduced, that is equal to 22.7 liters, because 1 bar is equal to 0.98 atmospheres. By this, you can write 1 atmosphere is equal to 0.98 bars. So it is bar is slightly higher than atmosphere. So automatically the volume will increase to 22.7 liters. I hope it is clear, because 1 atmosphere is equal to 1.013 bar, or you can say 1 atmosphere is equal to 0.98 bars. So this is 1 atmosphere is not equal to 1.0. 1 bar is equal to 0.98 atmospheres. So I hope it is clear. Next question. Next. So this is called molar volume of the gas. Now, Volume of a gas is the volume occupied by the 1 mole of a gas at a given condition of temperature and pressure is called, at a given condition of temperature and pressure is called molar volume of the gas. Next, relation between density and molar volume of the gas, as I already given you. From Avogadro's law, we know V is equal to K into N is equal to weight by molecular weight, because number of moles, 1 mole is equal to weight by molecular weight. So V is equal to K into weight by molecular weight. M is equal to K into W by V. Since W by V is equal to density, by this you can see M is proportional to density. So molar volume is proportional to density. Molar mass is proportional to density. So density is proportional to molar mass. So if the mass, molecular weight of a compound is more, automatically its density also more. I hope it is clear. Thus, under same conditions of temperature and pressure, the density of a gas is directly proportional to the density of a gas. We can write the density of a gas is directly proportional to the molecular mass of the gas. So higher the molecular mass of the gas, more will be its density. Higher the molecule, this sentence is important. So higher the molecular mass of the gas, more will be its density. Since already we have seen from gas equation also, D is equal to Pm by RT. By this what you can understand, density is proportional to pressure as well as molecular mass of the gas. So molecular mass. So more the molecular mass, molecular weight, automatically more will be the density. I hope it is clear. Next. So density of gas. As I derived this, so PV is equal to nRT, N is equal to weight by molecular weight, where W is equal to mass of gas, M is equal to molar mass of gas. So PV is equal to W by M into R into T, and P is equal to W by M is equal to D. So P is equal to DRT by M. So we can write W by V is equal to RT by M. So P is equal to D into RT by M. This already we have derived in this class. So by this we can write, by this we can write P is equal to DRT by M. R implies D is equal to density of a gas is equal to Pm by RT, because this M will go this side. So D is equal to Pm by RT. So there is a relation between density and molecular mass of a gas. So expression for density of a gas for combined gas equation we can write like this. I hope it is clear. So based on this formula also you'll get a question. And we have done one numerical also based on that. More numericals we'll do. Next topic in this chapter is Dalton's law of partial pressure. Very, very important. So from Dalton's law, definitely you'll get a question. So try to understand. Statement is easy, but doing numerical is difficult. So please listen carefully. Very, very important. Dalton's law of partial pressures. So what is Dalton's law of partial pressure? We'll discuss now. Statement is very easy. This law states that in a mixture of non-reacting gas, very, very important here, which of the following is not applicable for Dalton's law? If they are reacting, Dalton's law cannot be applicable. Non-reacting gas, very, very important. The gases which you are taking in a container, they should not react. If they react automatically, you'll get different. So definitely you'll get a product. For example, if you take if you take sulfur dioxide and oxygen gas in a container, definitely it will form sulfur dioxide. So for this, Dalton's law is not applicable. So if you are taking reacting gases mixture in a container, Dalton's law is not applicable. So for this, Dalton's law is not applicable. Dalton's law is not applicable for these two gases in a container. So that's why very, very important is reacting gas, non-reacting. So according to Dalton's law, the law states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressure of the individual gases. For example, you take three gases in a container. If you're in a mixture of n gases, n means some number of gases, the relation between total pressure is equal to partial pressure of first gas, second gas, third gas, and so on up to partial pressure of n gas. That's sum of the partial pressures of the individual gases. So the statement, as I told you, the statement is important. In that statement, very important is non-reacting gases. In a mixture of non-reacting gases in a container, the total pressure exerted by these gases is equal to the sum of the total pressure exerted is equal to the sum of the partial pressures of individual gases. This is called Dalton's law of partial pressure. I hope it is clear. So very important is non-reacting gases. The total pressure exerted by the mixture is equal to the sum of the partial pressure of individual gases. And finding partial pressure is more difficult because we have to consider mole fraction also for this. So this is called Dalton's law. Statement is easy, but the numericals based on this is a little bit tough. So partial pressure is nothing but what is the pressure exerted by the gas in the gaseous mixture. For example, you take three different gases, say oxygen, nitrogen, or hydrogen. If you take the three gases in a container, so for example, you take oxygen gas, nitrogen gas, and hydrogen gas at room temperature. At room temperature, these are not reacting. So in a container, then the pressure exerted by oxygen gas, pressure exerted by nitrogen gas, and the pressure exerted by hydrogen gas is equal to is nothing but partial pressure. So the partial pressure is exerted by the gas in the gaseous mixture. The partial pressure of a gas is equal to the pressure that the gas would exert if it is enclosed in the same volume and at the same temperature. So this is called partial pressure. And how to find partial pressure also we'll discuss now. So determination of partial pressure of dry gas in a moist gas. Because what is this moist gas? Here I'll add the statement. Since most of the gases, prepared in the lab, prepared in the lab, or obtained in the lab, prepared in the lab, in the chemical lab, are obtained by downward displacement of water. Downward displacement of water. Underline this statement, you have tried in your classwork. So downward displacement of water. Since most of the gases prepared in the lab are collected by downward displacement of water. In that they have moist gas also, means from water also exerts some pressure, so that is nothing but moisture. So determination of partial pressure of dry gas in a moist gas and determination of partial pressure in terms of mole fraction. So both gases it is important. So partial pressure can be determined by applying, we can find out the pressure of dry gas by using moist gas also, that is called aqueous tension. The pressure applied by water is called as aqueous tension. So we have to consider aqueous tension also into consideration. The pressure given by the water is called aqueous tension. So more about aqueous tension we'll discuss now. So these are the two applications of Dalton's law. We can determine the partial pressure of dry gas in a moist gas, as well as we can determine the partial pressure in terms of mole fraction. So these are the two applications of Dalton's law. I hope it is clear. Next. So how to determine partial pressure of dry gas? So the partial pressure of moist gas is equal to sum of partial pressure of dry gas as well as partial pressure of water vapor. As I told you, water also exerts some pressure. So it is partial pressure of dry gas and partial pressure of water vapor. Actually, whatever the pressure of the total gas is equal to, moist gas is equal to. So the saturated water vapor at a water vapor pressure at a given temperature is known as aqueous tension. So the pressure exerted by water is called aqueous tension. The saturated water vapor pressure at a given temperature is known as aqueous tension. So pressure of moist gas is equal to pressure of dry gas plus aqueous tension. Or you can say how to find pressure of dry gas. You can find out pressure of dry gas is equal to pressure of moist gas minus aqueous tension. So this is very, very important. So to find pressure of dry gas, partial pressure of dry gas, we have to use the formula partial pressure of moist gas minus aqueous tension. This formula came into existence since most of the gases are collected by downward displacement of water. So they have water and they have the pressure obtained due to water also. That is called aqueous tension. So this is very, very important. I hope it is clear. Next. What is mole fraction? Mole fraction is the ratio of moles of a given component to the total number of moles of all the components present in the mixture. So this already we know in stoichiometry or basic concepts of chemistry we have done this. In a mixture of three compounds A, B and C, the mole fractions of A are given by chi of A is equal to number of moles of A by number of moles of A plus B plus C. This is total number of moles. Similarly, chi of B is equal to like this and chi of C is equal to N of C. We call it as mole fraction of C. It is also chi. Chi means CHI, chi. So chi of A is equal to number of moles of A by total number of moles of the solution. Chi of B is equal to number of moles of B by total number of moles of the components. And chi of C is equal to number of moles of C by total number of moles. And how to find number of moles of A? Weight of A by molecular weight of A. So that also we know. Now, determination of partial pressure in terms of mole fraction. So in a mixture of gas, let us say P is equal to P1 plus P2 plus P3. This is the application of Dalton's law. That is, the total pressure exerted by the gas mixture is equal to sum of its partial pressure. Sum of its partial pressure, say it is P1, P2, P3. So how to find P1? P1 is equal to N1 RT by V. From ideal gas equation, we know PV is equal to nRT. So volume becomes same volume for all the three gases. So 1 liter capacity, 10 liter capacity container. So volume becomes same. So we can take P1 is equal to N1 RT by V, P2 is equal to N2 RT by V, and P3 is equal to N3 RT by V, where N1 and N2 and N3 are called number of moles of each gas. So by this you can write PV is equal to, since RT is common in all the cases, we can take total pressure is equal to number of moles of first gas plus number of moles of second gas plus number of moles of third gas into R, that is universal gas constant, into T by V, into T by V. So by this you can say P is equal to N1 plus N2 plus N3 RT by V. Next, on dividing P1 by P, total partial pressure by total pressure, we will get N1 by RT by V plus N1 plus N2 plus N3 by substituting the values, you will get mole fraction. So by this you can say P1 is equal, because n RT by V gets cancelled. So in this case, RT by V and RT by V gets cancelled. So we can say only N1 by N1 plus N2 plus N3. So it is equal to mole fraction. So by this you can say P1 by P is equal to mole fraction of first gas. So by this you can say partial pressure is equal to mole fraction into total pressure. This formula is very important. So partial pressure is equal to total pressure into mole fraction. If they are given number of moles directly, we can find out the total pressure and we can find out partial pressure. So these two formulas are important. So how to find total pressure? Total pressure is equal to N1 plus N2 plus N3, if there are three gases, into RT by V. This is the formula for finding total pressure, and we can find out partial pressure also. So these two formulas are very, very important. Next. That's what I told you. Dalton's law statement is easy, but numericals are a little bit tough. Now let us see example 1. Neon dioxin mixture, neon gas. So it is neon gas as well as dioxin mixture. Contains 70.6 grams, 70.6 grams of dioxin. So weight of oxygen is given. It is given as weight of dioxin, and 167.5 grams of neon. Weight of neon is given. If the pressure of the mixture of the gas in the cylinder is 25 bars, total pressure is given. What is the partial pressure of dioxin and neon in the mixture? So total pressure is equal to sum of the partial pressures P1 plus P2. But what is P1? P1 is equal to N1 RT by V. And what is P2? N2 RT by V. So by this you can write P is equal to N1 plus N2 RT by V. So number of moles. And how to find number of moles by using this? They have given weight only. They have not given number of moles directly. They have given weight. So from this you can find N1 is equal to I'll just clear it again. I'll explain this problem clearly. In this case, they have given mixture of neon as well as dioxin gas weights they have given. They have given important partial pressure. So total pressure they have given of the mixture of these gases in a cylinder. So what is the partial pressure of dioxin? So to find partial pressure is equal to of oxygen is equal to mole fraction of oxygen into total pressure. Similarly, partial pressure of neon is equal to mole fraction of neon into total pressure. So how to find mole fraction? Mole fraction is equal to mole fraction of oxygen is equal to number of moles of oxygen by number of moles of oxygen plus number of moles of neon. Similarly, mole fraction of neon is equal to number of moles of neon by number of moles of oxygen plus number of moles of neon. So in this case, you have to find. But how to find number of moles of oxygen? Because number of moles of oxygen is also not given. So to find number of moles of oxygen is equal to weight of oxygen is given 70.6 divided by total weight is given. Oxygen molecular weight is 32 grams. Similarly, neon, number of moles of neon is equal to weight of neon 167.5 grams. That's why I told you this is very, very big numerical. Calculation part is more. By number of weight of neon is 167.5 grams. Molecular weight of neon is 20. So you can find out the values of N of O2, N of Ne. From this you can find out X of O2, that is mole fraction of oxygen, mole fraction of neon, and substituting mole fraction of oxygen in partial pressure of oxygen into total pressure is given 25 bars. This is called total pressure P, 25 bars. So first you have to find mole fraction of oxygen, mole fraction of neon, and from this you can find out mole fraction of oxygen, mole fraction of neon. So automatically you'll get the answer. I hope it is clear. So you'll get the answer. Partial pressure of dioxin will be in bars as well as 5.2 bars, 19.8 bars. So here we have to calculate first step. Again I'm writing here. First we have to calculate mole fraction of oxygen. Second we have to calculate mole fraction of neon. How to calculate mole fraction of oxygen? Number of moles of oxygen by number of moles of oxygen plus number of moles of neon. And how to find number of moles of oxygen? Number of moles of oxygen is equal to weight of oxygen, that is 70.6 divided by 70.6 divided by 32, because molecular weight of oxygen is 32. Similarly, number of moles of neon, how to find? Number of moles of neon is equal to, number of moles of neon is equal to weight of neon is given 167.5 grams by 20, because molecular weight of neon is 20. So by substituting these values, you can find out mole fraction of oxygen, mole fraction of neon, mole fraction of neon. So once you get mole fraction of oxygen, you can find out mole fraction of neon. After finding mole fraction of oxygen and neon, we can use the partial pressure of oxygen is equal to total pressure, capital P, into mole fraction of oxygen gas. Similarly, partial pressure of neon is equal to total pressure, that is capital P, into mole fraction of neon. So by using this formula, you'll get the answers. I hope it is clear. Very, very lengthy problem, but in the exam, they'll give you simple problems. So next what we have to do in this chapter, some more numericals based on Dalton's law will do. So then we can end up this session based on Dalton's law and numericals. Yes. Now, some more numericals. A mixture of hydrogen and oxygen at 1 bar pressure contains 20% of hydrogen by volume. They have given 20% of hydrogen by volume. So, since we know, so it contains hydrogen and oxygen, and total pressure is given 1 bar pressure. So, what is the partial pressure of hydrogens? Very simple problem. Since volume is proportional to number of moles, if we take 20% of hydrogen by volume, so number of moles of hydrogen is equal to 20, and number of moles of oxygen is equal to 80. 20 by 100 and 80 by 100. Sorry, 80 by 100. So which is equal to, so mole fraction of number of moles of hydrogen is equal to 0.2, and this becomes 0.8. So straight away you can take, so partial pressure of hydrogen is equal to simple total pressure into mole fraction of hydrogen gas. So that is equal to total pressure is 1 bar. It is given 1 bar. So 1 into directly number of moles also you can take 0.2. So it is equal to 0.2 bars. Similarly, partial pressure of oxygen also we can find partial pressure into mole fraction of oxygen gas. So we can take 1 into 0.8. So it is equal to 0.8 bars. So by this you can take P is equal to, you can verify also P is equal to 0.2 plus 0.8, which is equal to 1 bar. So this is called verification. I hope it is clear now. Next question. Because since volume is proportional to nitrogen by Avogadro's law, by applying Avogadro's law directly, we can take number of moles. So the answer is partial pressure of hydrogen is equal to 0.2 bars, and partial pressure of oxygen is equal to 0.8 bars. Next question. A mixture of nitrogen and oxygen is maintained at a total pressure of 50 bars. So they are given total pressure P, capital P. The mixture contains 192 grams of oxygen and 280 grams of nitrogen. Calculate the partial pressures of oxygen and nitrogen in the mixture. Since they are given weight, first you have to find number of moles. So number of moles of oxygen is equal to 192 by 32. Similar number of moles of nitrogen is equal to 280 by nitrogen. What is the molecular weight of nitrogen? 28. So we can find number of moles of oxygen, number of moles of nitrogen. After finding number of moles, we can find first mole fractions of oxygen is equal to number of moles of oxygen by total number of moles of the mixture, that is number of moles of oxygen plus number of moles of nitrogen. Similarly, after finding mole fraction of oxygen, we can find partial pressure of oxygen is equal to total pressure, that is P, which is equal to 50 bars into mole fraction of oxygen. Similarly, partial pressure of nitrogen is equal to total pressure into mole fraction of nitrogen. How to find mole fraction of nitrogen? Mole fraction of nitrogen is equal to number of moles of nitrogen by number of moles of oxygen plus number of moles of nitrogen gas. So from this you can find mole fraction of nitrogen, and from this you can find mole fraction of oxygen. After finding how to find number of moles of oxygen and nitrogen, you can use weight by molecular weight. So after getting, you can find partial pressure of oxygen, partial pressure of nitrogen, because total pressure they are given 50 bars, 50 into mole fraction of oxygen, 50 into mole fraction of nitrogen. So I hope it is clear. So this type of questions are important for all competitive exams. This is the application of Dalton's law. So partial pressure of oxygen becomes 18.75 bars, and partial pressure of nitrogen becomes 31.25 bars. More important, if you apply Dalton's law, whether it is correct or not also you can find out easily, because P is equal to P1 plus P2 we can find out. So this should be equal to 50. Implies P1 plus P2 is equal to 50 you should get. How much you should get? 50. So by adding these two, we'll get 50 only. So hence it is correct answer. I hope it is clear. So this problem is most important. Next question. Find the total pressure exerted by 32 grams of methane. Here also they are given weights, and 22 grams of carbon dioxide contained in a 4-liter flask. Here this model is different. They have given volume. Also calculate the partial pressures. First we need to find total pressure, then we have to find partial pressure. So for this to find total pressure, P is equal to N1 plus N2, because two gases, that is methane is N1 and methane as well as, so they are given methane as well as carbon dioxide. So N1 plus N2 into RT by V is a formula for finding total pressure. So it is equal to N1 is given 32 grams. So first you have to find N1. So N1 is equal to weight by molecular weight, 32 by 16, because molecular weight of methane is 16, is equal to 2. Similarly, N2 is equal to 22 by 44, because molecular weight of carbon dioxide is 44, it is equal to 0.5. So by this you can write 2 plus 0.5 into R value is given 0.0823, 0.0821 into temperature 27 degrees C. 27 degrees C means 300 kelvins. Here I'm writing into 300 divided by volume is given 4-liter flask 4. So it is equal to 2.5 into 0.0821 into 300 divided by 4. So after doing this, you will get the value 2.5. I'm calculating here 2.5 into 0.0821 into 300 divided by 4 is equal to 15.39. So answer is exactly 15.39 atmospheres. approximately. Next, total pressure is equal to this. Now, after finding total pressure, we can find partial pressure. Partial pressure is equal to partial pressure of methane gas, CH4, is equal to total pressure into mole fraction of methane gas, that is CH4. And how to find mole fraction, we already know. Mole fraction is equal to mole fraction of methane is equal to, I'm writing it here since we do not have place, number of moles of methane by number of moles of methane plus number of moles of carbon dioxide, that is equal to 2 by 2 plus 0.5, that is equal to 2.2 by 2.5. So 2 divided by 2.5, you get it as 0.8. So partial pressure of methane is equal to total pressure of methane is given how much? We already got is 15.39 into 0.8, that is equal to 15.39 into 0.8 is equal to 12.312, approximately 12.312. Similarly, partial pressure of, so mole fraction of methane is given. So we can find mole fraction of carbon dioxide, that is equal to 1 minus 0.8, because total mole fraction of two components is equal to 1. So it is equal to 0.2. So partial pressure of carbon dioxide is equal to total pressure, that is 15.39 into 0.2, 0.2. We can find out 0.2, which is equal to 15.39 into 0.2, 3.078. So 3.078. So approximately this is partial pressure of carbon dioxide, partial pressure of methane gas. I hope it is clear. So first we have to find total pressure by using the formula number of moles of the mixture of the gases, total number of moles of the mixture of gases into RT by V by applying Avogadro's law. So RT by V. So P is equal to nRT by V. So where N is equal to N1 plus N2. So N1 is equal to 32 by 16, N2 is equal to 22 by 44. So 2 plus 0.5 into R value is 0.081 into 300, which is coming around 2.5 into 0.081 into 300 by 4, and it is equal to 15.39. So first we have to find total pressure. In this everything we have to find total pressure. We have to find. After finding total pressure, we can find partial pressure by finding mole fraction. From number of moles, we can find out mole fraction by using this formula. So mole fraction of methane is equal to number of moles of methane by number of moles of methane plus number of moles of carbon dioxide. So this is called number of moles of methane. This is the number of moles of carbon dioxide. So we can find out like this. So very simple problem, but it will take more time for calculation. But in the examination, they'll give calculation part easily. So partial pressure of methane is equal to 12.3, as you already got. Total pressure is equal to 15.39 approximately. Partial pressure is equal to 3.078 of carbon dioxide. So it is very, very important model. I hope it is clear. Next question. Very, very important. In an experiment, hydrogen gas is collected over water. Since already I told you many gases are collected over water at a pressure of 650 mm. So they are given pressure also. They are given pressure and at temperature T as well as pressure. So the aqueous tension at 300 kelvins means that is pressure due to water is equal to aqueous tension is equal to how much? It is 27.5 mm. Calculate the pressure of dry gas. Simple it is. So pressure of dry gas is equal to pressure of moist gas minus aqueous tension. Minus aqueous tension. So what is the pressure of moist gas? Pressure of moist gas is equal to, they have given 650 mm. Minus aqueous tension is how much? 27.5. So it is equal to 622.5. I'll take, I don't need it because it is more visible. Sorry. 622.5 is the answer. So whenever they are given aqueous tension, we have to minus it from moist gas. That's all. Because pressure of dry gas is equal to pressure of moist gas minus aqueous tension. I hope it is clear. Let us check the answer. So it is 622.5. I hope it is clear. Next question. Calculate the density of sulfur dioxide at 320 kelvins and 2 atmospheric pressure. Very important. This already we have done. So to find density is equal to P into molecular weight by R into T. Simple formula. So what is pressure is given to atmosphere. Molecular weight of sulfur dioxide. Sulfur dioxide is 32 plus 32. Sorry, it is 64 because sulfur is 32 plus oxygen is 32 is equal to 64. So 2 into 64 divided by R value is 0.0821. 0.0821 into temperature is given how much? 320 kelvins. Directly they are given kelvins temperature. So substituting this formula, you will get 2 into 64 is 128 divided by 0.0821. That is 0.0821 into 300 into 320 is equal to 26.272. So it is equal to 128 divided by 26.272, which is coming around 4.87 approximately. So this is the density 4.87 grams per liter. Grams per liter is the answer. Let us check this answer now. So it is 4.878 grams per liter. I have taken only one decimal. They have taken 3 decimals. That's all. So 2 decimals. I hope it is clear. So this formula is most important. They'll ask in the competitive exams. D is equal to PM by RT, where P is called pressure, M is called molecular weight of the gas, R is called gas constant, universal gas constant, T is called temperature. I hope it is clear now. Next question. The density of phosphorus vapor at 327 degrees C. Actually, it should not 3270. It should be 327 degrees C. I'll correct it now. So this is taken as 327 degrees C. And 1 atmospheric pressure is 2.52 grams per liter. What is the molecular formula of the phosphorus under these conditions? So you have to find the molecular weight of phosphorus. Automatically you'll get the answer. So from the formula, D is equal to PM by RT. If you find the molecular weight more, then you'll get the formula of the compound. So M is equal to DRT by P. So what is density is given 2.52 grams per liter into R value is 0.0821. Temperature is 327 degrees C, means T is equal to 327 plus 273, which is coming around 600. So into 600 kelvins divided by pressure is given how much? 1 atmosphere. So straight away 1. So if you multiply this, you'll get the answer. So 2.52. I'm doing the calculation now. 2.52 into 0.0821. 2.52 into 0.0821 into 600 is equal to 124, approximately 124. Now, since phosphorus weight is 31, so formula of phosphorus is equal to 124 divided by 31. 124 divided by, because phosphorus atom is 31. So 124 divided by 31 is equal to 4. Implies the formula of the compound is P4, phosphorus 4 molecule. I hope it is clear. So P4, 124 by 31, it is equal to 124 by 31 is equal to 4. So each phosphorus is 31, already we know. So number of phosphorus in that condition in the molecular formula is total number of 4 phosphorus atoms are present. How many atoms? 4 phosphorus atoms. So the molecular formula of the phosphorus is, from this condition, it is equal to P4. I hope you understood the concept. Let us check the answer now. So it is P4. As I told you, it is P4. Clear now? So D is equal to Pm by RT. They are asking molecular formula of phosphorus. So for finding molecular formula, we have to find molecular weight. So to find molecular weight, you can use the relation D is equal to Pm by RT. So M is equal to DRT by P. Density is given 2.52. R value, universal gas constant is equal to universal gas constant is equal to 0.0821, and temperature value is 600, and pressure is given 1 atmosphere. So 600 kelvins, because they are given 327 degrees C. It is not 3270. It is printing mistake. So 327 degrees C. So it is equal to 327 plus 273. Always you have to change the temperature into Kelvin only, because all the gas laws are nothing but based on Kelvin temperature. That is absolute temperature. So I hope it is clear now. Next. So by this we have in this session we have done Avogadro's law, Dalton's law, and problems related to gas laws. I hope it is clear. More problems we'll do in the next session. And after this next session, we'll take new topic. And at the end of the chapter, we'll take all the numericals, more and more numericals, especially for NEET and JEE mains. Thank you all. I'm closing the class. So I'm stopping the class now. Thank you.